All right, ladies and gentlemen, today's class recording has started. And if you're so close to the microphone and talking, it'll definitely pick you up. So I meant more that I didn't want. I meant more that I didn't want you to talk. So even though where I said, "Hey, today's class recording has started," okay. All right. Yesterday we talked about, and we didn't. I didn't exactly preface it this way, but we talked about the difference between constant velocity versus constant acceleration. So, describe to me what is the difference between constant velocity versus constant acceleration. Eric, go ahead. Good. Constant velocity, same speed, certain direction, right? Just like this picture right here. We talk about that the object moves the same displacement every time, velocity being a relationship between displacement and time. So if it's the same displacement every time, we have a constant velocity. But then we talked about this bicycle rider here, right? Who we can tell just from the pictures and how they're spaced, appears to be speeding up, and then when you add the velocity values in here, right, we can see that he's speeding up, but more importantly, each time or each second that goes by, his velocity increases by the same amount. Remember, acceleration tells us about how much does the velocity change, right? So in this case here, going from this picture to this picture, the velocity jumped from 0 to 2. From here, it jumped from 2 to 4. He's obviously going faster, but it changed by the same amount, and that's important. So every time we analyze how much does the velocity change during a given period of time, it always changed by the same amount, and so that tells us that the acceleration is constant. Okay? Good there. Okay with those ideas? All right. Let's add the third sort of descriptor of motion in here, or sorry, I guess the fourth, right? This one here, when we talked about constant acceleration, obviously we talked about acceleration, that it was accelerating. We talked about velocity because we analyzed how the velocity was changing, and we talked about time because we talked about how much time passes as we go along. So, there's the fourth thing, the fourth descriptor of motion that we've talked about that we haven't quite addressed yet, and that's the displacement, or how far does this object go, right? You guys have this extra detail on your picture, right? So let's talk about where those numbers come from today, and that's what our focus for today is. As an object is accelerating, how far does it go while it's accelerating? Does it make sense that because he's speeding up, each second that goes by, he keeps going further? Are we okay with that? Are we okay with that, at least conceptually? That if he's going faster, if we look at how far he goes each time, he's going to keep going farther because he's going faster. Good? All right. Well, let's talk about how far does he actually go. And we're going to start by analyzing this little interval right here. Okay? So, we talked yesterday and we showed that the acceleration here was 2 meters per second, right? How come the acceleration during that interval is 2 meters per second? Explain it to me. Why is that the acceleration? Jack, go ahead.
Because by acceleration you change in velocity over time.
Good, change in velocity over time.
And the change in velocity is 2 meters per second.
Okay.
And the time is 1 second.
Good.
2 divided by 1 is 2.
So the velocity changes by 2 every second, right? You good there? Okay. Now, let's talk about this velocity. I believe yesterday we had a discussion and some of you were confused at the beginning because it says here that the velocity is 2 meters per second, but down here it shows that the bicycle only went 1 meter. And some of us were confused with that. Well, wait a second. When we did this picture, right? Every second that went by was 1 meter, and therefore the speed was 1 meter per second. So how come here it's telling me the speed is 2, but it only went 1 meter, right? And what did we say the answer to that question was? How did we resolve that sort of discrepancy? Debbie, go ahead. It has to do with instantaneous velocity versus average velocity, right? 2 meters per second is the instantaneous velocity. That's how fast it's going at that particular moment in time. But what was it doing the entire time, or what was it doing? Does he need that? Or?
Joe, do you need this?
Why don't you take it with you, just in case. So, just in case. So. All right. 2 meters per second is the instantaneous velocity, what it was doing at that particular moment. But what was it doing up until that point in time? Accelerating. Was it going faster or slower than 2, Ellen? Slower. It gradually sped up until it got to 2. Okay? And if it took a whole second to get from 0 to 2, we can assume, if it's constant acceleration, it was a nice gradual increase. So if we took a picture of this bike rider, let's say instead of at 1 second, let's say we took a picture at 0.5 seconds, what would the velocity have been a half a second after he started pedaling his bicycle? 1 meter. Because we're talking about velocity, right? So his velocity would have been 1 meter per second or at that time. Are we okay with that? Okay with that idea? Okay. So let's talk about how we get this 1 meter. Okay? Averages, right? Let's talk about averages. How do we calculate the average of something, just in general? Right? Right. Add them all up and divide it by the number that we know of, right? Okay? So, let's talk about velocity during this time, okay? Forget the extra one that I wrote up on the top, just the 2 that they gave us. How many instantaneous velocities did they give us within that interval that I've highlighted in yellow there? They gave us 2, right? They told us what the initial velocity was, and then they told us what the final velocity was during that time, okay? Those are both instantaneous, happening at a particular moment, but we can figure out the average from that information, right? So Frank, applying our definition of average to this situation, if we started off at 0 velocity and ended up at 2 velocity, what was the average of those 2 numbers? 1. Right? So, in this case here, the average velocity during this interval is 1 meter per second. Does everybody see where I got that number from? You okay with that? Okay, actually I should do this. Okay? Good with that. All right. Now, how do we get from average velocity to showing how far we went? Well, we actually wrote down our definition for average velocity at the very beginning of our discussion yesterday. All right? Does anybody remember how one way that we can calculate the average velocity? How do we define velocity? Hint, it's up on the board. Delta x divided by t. That's our definition of velocity. Are we okay with that? Okay. Well, this is velocity, right? Yeah, it's an average velocity, but it's still velocity, right? So using that definition, we can figure out how far this bike rider went using that definition. Sorry. All right. What did we say the average velocity was during this interval? 1 meter per second. So I'm going to plug 1 in there for V. What are we trying to verify here? So we're trying to figure out how far the guy went, right? Sorry, I didn't know if we remembered that, right? So technically, we'll call that X. That'll be our variable, right? What time frame are we talking about here? Just in that section that I have circled. 1 second. All right. Can we solve that equation for X? I hope so. All right, okay. So what would X be in that situation? 1. And how far did it tell us that we went during that interval? 1. Good there? Okay. That's easy. There's lots of 1s. All right? Let's talk about this interval. Okay? Let's talk about that interval right there. Okay. We've already verified, but just in case, what's the acceleration during that interval right there? All right. 2 meters per second, right? Because how much does the velocity change, Alec? Goes from 2 to 4, so 2 meters per second for every 1 second. Okay? Good there? All right. Now, let's take this next step. What is the average velocity during that interval? Frank? 3. The average velocity during this interval is 3 meters per second. Everyone see where Frank got that from? If you don't, raise your hand. Don't be a chicken, just raise your hand. Okay, all right. Frank, how do we calculate the average of something? Well, in any case, we add them up and divide by the number, right? Okay, so we're averaging velocities. During this interval that I've circled, how many velocities did they give us to work with? 2. Right? And they were 2 and 4. Right? Frank, if we add 2 and 4 together, what do we get? 6. But then to calculate the average, what do we have to do with 6? Divide by 2, because that's how many velocities we're dealing with. 6 divided by 2 is 3. Does that make sense? Okay. Now, going back, we know that velocity is a relationship between displacement and time. So during this interval that I circled in blue, right, what did we calculate was the average velocity? 3. So I'm going to plug 3 in here. We're trying to figure out or verify how far he went. So that's going to be my variable. I'm going to call that x. And then this interval that I've circled, how much time are we talking about? 1 second. Because it went from time 1 to time 2. Does that make sense? If we solve that equation, what's x? 3. So that means from here to here was 3 meters. Does that make sense? We okay with that? And that means the total distance from the start is now what? 4. We okay? Is that good so far? Let's do one more example here. All right? So let's go there to there. Okay? What's the acceleration value? during that interval that I've circled in green. Good. What's the acceleration value? Let's go step by step. How much does the velocity change? 2, right? And how long does that take? Time-wise?
No, that's 1 second.
1 second. Don't listen to them.
Yeah, that was great.
So here, the velocity goes up from 4 to 6, and that takes 1 second, so that means our acceleration is what? 2 meters per second. Okay? Good there?
No.
So, acceleration, right, tells us about how much does the velocity change per time. Okay? So just this section that I circled in green, right? The velocity goes from 4 to 6. So, how much does the velocity change during that time? 2. It goes up from 4 to 6. So delta V is 2 meters per second, because that's how much the velocity changed. And then, how much time passed during that interval? 1 second. So that's where we get the 2 meters per second. Okay? Good there? All right. Now, Julia, the first thing that came out of your mouth when I asked you the acceleration was what? 5. 5 is not the acceleration, but 5 is something important here. What is 5 during this little interval?
Yeah.
The average velocity. Good. The average velocity during this interval is 5 meters per second. And how did you get that, Julia? Added 6 and 4 and divided by 2. Okay? So that's the average. It gradually sped up from 4 to 6. And 5 being right in the middle, that's going to be the average, right? Half the time it's below 5, half the time it's above 5, that makes the average 6, or that makes the average 5. You okay with that? Okay. And then, that being said, right, if we know that average is delta x, or sorry, velocity, if velocity is delta x over t, right, what did we say the average velocity was? 5. We're trying to find how far it goes in 1 second, and that means that the distance from here to here is 5 meters. Okay? Good so far? Okay. Let's apply these concepts to a new situation. Okay? Flip it to the next page, or the back of the first page in your packet. And let's take a look at the second one down. Okay? So, here's a picture of a ball rolling down a ramp. Okay? The ramp is tilted so that the acceleration that the ball experiences is 4 meters per second squared. Okay? So, that being said, if we know the acceleration is 4 meters per second squared, what is that telling us? Don't massage yet. If the acceleration is 4 meters per second squared, what does that mean is going to happen, or what is that telling us? Well, what does acceleration explain for us, or what does acceleration describe for us? Change in velocity. If the acceleration is 4 meters per second squared, what does that mean? How about instead of each position, Sammy said at each position it's going to be 4 meters per second faster. Each second it's going to be 4 meters per second faster, right? 4 meters per second squared is the equivalent of 4 meters per second, right? Is that okay? All right. So in this picture, just like the picture of the bicycle rider from the previous one, these pictures each represent where the ball is at 1 second intervals. Okay? Where the ball is at 1 second intervals. So, up here at the top of the ramp, this is time 0. This is right when we let the ball go on the ramp. Okay? And at the very instant we let the ball go on the ramp, what is it telling you the velocity was? At the very instant we let it go, the velocity is 0. But as soon as we let it go, what starts happening? It accelerates. Specifically, it's doing what in this case?
Speeding up.
Going faster, speeding up. Okay? The next picture is t equals 1 second. 1 second later. Sammy, based on this acceleration value, what will the velocity be at that point in time? Or, sorry, what will the instantaneous velocity be at that point in time? 4 meters per second. Does that make sense? You okay with that? Give me a nod if we're okay. All right, so we know in that case, the velocity is going to be 4. All right? I'm just going to write 4 because if I write units, it gets a little bit sloppy because it gets all kind of, so I'm just going to write 4. But make sure we know that if the velocity, if you can write it, cool. Okay. All right. The next picture is 1 second later. So that would be t equals 2. What's the velocity going to be, Frank? The instantaneous velocity is going to be 8 meters per second. Frank, how do we know that? Good. That means the velocity has to do what in that amount of time? Go up by 4, or more specifically, more generally, change by 4, but in this case it's going to go up, right? All right, next picture. 3 seconds after we let it go. What's going to be the velocity at that point in time? 12 meters per second. The instantaneous velocity is 12. Right? And then the next one, what's the instantaneous velocity going to be? 16. And then finally, when it gets to the end of the ramp, what's the instantaneous velocity? 20 meters per second. Good with all those numbers came from. So now we know instantaneous velocities. Let's talk about distances. Clearly, in the picture, right, and we talked about, if this ball keeps going faster and faster and faster, that means that it's going to go farther each second, and that's what the picture is showing us here. But let's talk about how much farther. So, let me start with this interval right here. Okay? That first interval from 0 second to 1 second. Actually, I should do this. Hold on. I'll just highlight that little section right there. Okay? All right. We've already established that the acceleration during that time is 4 meters per second squared. It's constant acceleration the whole ramp. What is going to be the average velocity of the ball during that interval? The average velocity during that time, Jack, is
2 meters per second.
2 meters per second. Okay? Anyone not know where 2 meters per second came from? If you don't know, raise your hand. Okay? So, to find the average, Frank, to find the average of anything, what do we do? Add the two numbers and divide by how many there are, right? So during that orange interval, we know two velocities, right? What are the two velocities that we know? Just in that orange interval.
0 and 4.
Good, 0 and 4. Does that make sense? And if we add those two together, we get, well, we add 0 and 4 together, we get what? And then we divide by 2, and that gives us 2. Good? Okay? Does that make sense? And then, but that's not what it asked us for, right? We want to know how far did it go? Velocity is displacement over time. What do we know the average velocity was during that interval? 2. We don't know how far it goes, that's our variable, but we do know how much time passes. 1 second. And that means that the amount of distance that that travels, or the displacement during that time, is how far? 2 meters. Okay? Good there. All right. Let's talk about, there it is, pink interval. Okay? So, average velocity of the pink interval is 6 meters per second. Do we understand where the 6 came from? Okay? Okay? So during this pink section, right, the average is equal to 6. Okay? Julia, do you want the next question? Okay. So if the average is 6, how far did it go during that interval? 6 meters, because how much time are we talking about here? 1 second. So that means this interval right here is 6 meters. Good? You okay with that? Alright. Green interval. Average velocity is what? 10. And that means, Christina, the displacement during that time interval is going to be 10. Alright. So this is 10. Okay. And then, you okay with that? No, sorry, Alec. Alec was making a funny face, like I was like, oh, I better stop here. So, all right, and that means then, what would be the distance that the ball travels during the next interval? How far would it go from here to here? Not 4 meters. 14. Does that make sense? Why? Yeah. Okay. And that means that it would go, this time, it would go how far? You tell me what the last one is. Did you write it down? Alright. Good there? And that means the whole ramp is how long? Is that what it is? Yeah. I'm pretty sure that's what it is. That means the whole ramp is 50 meters long. Good with that? All I did was just add up all the little intervals. Okay.
To find the full ramp, you also do like.
All right, hold on. Don't ruin my surprise. All right. Okay. Good with that?
Yeah.
All right. One more for today. Next ramp. Even though it doesn't look like it from the picture, this ramp is tilted a little bit steeper And so now the acceleration is 5 meters per second squared. And if the acceleration is 5 meters per second squared, what does that mean? Frank, go ahead.
That the change in velocity is 5, and time is 1.
Okay. Every second that goes by, the velocity changes by 5 meters per second. Good there? Okay. Again, at the very, very top of the ramp, t equals 0, velocity is 0, and that means 1 second later, sorry, ultimately, we are trying to find how long this entire ramp is. Okay? So with that being said, let's go through the process, right? 1 second after we let it go, how fast will it be going? What will be the instantaneous velocity 1 second after we let it go? 5 meters per second. 2 seconds after we let it go, instantaneous velocity will be 10. 3 seconds, 15, 20, and 25. Okay, so now, let's apply what we've learned to make this task a little easier. Okay? Or save us some steps. In the last picture, we calculated how far the ball went at each consecutive second and then added all those numbers up. Okay? But because this is constant acceleration, all of those relationships that we talked about are true for 1 second intervals, but they're also true for larger intervals of time. So, let's take a look at the whole ramp. What is the average velocity for the entire ramp? Chris? Nope. There's 6 numbers there because you have this one that you have to add in. Okay? The average velocity for the entire ramp is 12.5 meters per second. Okay? 2 ways we could have done that. What did you do? You added all of them up, right? So, 0, because you got to include that one, plus 5, plus 10, plus 15, plus 20, plus 25, gives you 75, right? And then you divide that not by 5, but by 6, because you have to include that 0. Okay? That's perfectly fine. You can do that. But we can even make it simpler. Because we know that this is increasing by a nice even rate the whole time. We can figure it out just by looking at the beginning and the end. Just like we did for each of these little intervals. Alright? Here, the first interval we did on the previous picture, we added 0 and 4 and divided by 2. Here, I'm going to add 0 and 25, and then divide by 2. And I get average velocity at 12.5. Does that make sense? Yeah? Now, let's talk about what we're trying to figure out. We're trying to figure out how long this ramp is. Same procedure. We know that velocity is a relationship between displacement and time. Good? Yes, so far? Okay. What if we calculated was the average velocity the entire time this ball is rolling down the ramp? 12.5. So I'm going to plug in 12.5 here. I I don't know how far the ramp is, so I'm going to plug question mark in there. But here's where it becomes a little different. That 12.5 that I plugged in is for the entire ramp. So what time do I have to plug in to that equation? 5 seconds. Because I'm not just talking about one interval of that ramp, I'm talking about the whole ramp now. And it takes 5 seconds to get all the way down the ramp. Does that make sense? So we can look at average velocities over 1 second intervals, or we can look at them for the entire interval that we're doing. As long as we're talking about constant acceleration, it works. And so, Chris, that means the entire ramp is how long? 62.5 meters long. Does that make sense? You okay with that? Okay. So now we see how the relationship acceleration causes velocity to change. And that means the displacement each second changes as well, because that's how velocity is related to displacement. But now we see how a change in one causes a change in all the other ones, right? We will continue on with this tomorrow, and we'll talk about a specific type of acceleration, that being the acceleration of gravity.